This video lesson's on buffers and a little bit more about the notes that we began in class. This slide is the one we're going to start out, and the question right there on the top is why buffers even exist? What makes them so special? We talked about it, but now I'm going to show you using calculations and math. We talked about how buffers resist changes in pH drastically. And I've got two scenarios down here. I'll zoom in on one at a time to kind of highlight each one. I'll show you how it resists changes in pH. So let's actually talk about this one first. If you just take regular old water, 1 liter of it, it's at a pH of 7, which is identified here in this beaker. Now add 5 milliliters of 0.4 molar. You'll notice that the concentration goes down, or goes up, because it's a base. You can calculate this quite easily. Since the base is being added straight to water, the first thing we need to do is take the 4.0 moles per liter, which is 4.0 moles over liters, and multiply it by the volume of 0.005 liters to figure out how many moles of the base is in that 4 molar sample. After doing a quick calculation, take the volume times the molarity and you get the number of moles. The answer is 0.02 moles of NaOH. Now take the number of moles and divide by the new liters. There was 1 liter initially, and you added 5 milliliters to it. So you now have 1,005 milliliters, or 1.005 liters. The answer in molarity is 0.0199 molar, which is about 0.02 molar. Since this is the concentration of the OH, this was a strong base, this is the concentration of the OH. If I take the negative log of 0.0199, I will get an answer of 1.70. But keep in mind, that's the POH, because I take the negative log of a base, that's the POH. And if I take 14 minus the POH, I'll get the pH. If I take 14 minus 1.70, I get 12.30, which matches what we see over here in this little picture on the left. Simply adding a strong base to water drastically changes the concentration of OH in solution, and the pH changes pretty quickly. Now let's contrast that with this scenario over here. Now we're going to take the same 0.02 moles of NaOH, and we're going to drop it into a buffer, 1 liter of buffer, which is made up of 0.3 molar weak acid and 0.3 molar of its conjugate base. Now in order to do this problem, it's a little bit more complicated than the last one. You can't just take the negative log concentration, because we got to figure out that base is going to react with one of the two chemical species inside the buffer. A base will react with the acid. So what I want to do first is actually write out the chemical reaction of the buffered system. So you've got the acid, and I have 1 liter of 0.3 molar, or essentially I have 0.300 moles of this stuff, and I have 1 liter of 0.3 molar this, or I have 0.300 moles of this stuff. Now you got to think about the stoichiometry a little bit, because when this goes into the solution, it's going to reduce this by 0.02 moles. It's going to neutralize some of the acid in the buffer. And if I subtract 0.3 minus 0.02, I should get 0.280. But for every mole of this that gets lost, I gain a mole of this. So if this change is in minus 0.02 moles, then I gain 0.02 moles, and the plus 0.02 to this side gives me 0.320 moles of my conjugate base. Thinking about it a different way, the base comes in and soaks up some of the acid. The acid gets converted to conjugate base. So my concentration of my acid goes down, my concentration of base goes up, but my new solution will be out of, once again, 1,005 or 1.005 liters each. So if I calculate the concentrations of each of my chemical species now, the first one is 0.279 molar, which is about the same, but not quite. And the other one is 0.318 molar, and that's of the base, the conjugate base, and this is of the original acid. Now I need to calculate the pH. There's two ways to do this. There's the hard way and the easy way. The hard and most cumbersome way is using an ice table, but I'm going to introduce to you something called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch is a nice way, and it's a very easy way, and it basically shortens up an ice table. And it's listed on your yellow sheet, and here's the formula. The pH of a buffer is equal to the pKa of the buffer plus the log of the base divided by the acid. You have to take base over acid in parentheses and take the log of that. Now pKa, that might look new to you, but that's nothing more than taking the negative log of the Ka gives you the pKa, just like pH is the negative log of H plus. So the Ka is listed for you in the problem, or it'll be given to you, and you've got concentrations of base and acid, so all you need to do is plug these in and solve. Now it didn't list this in this problem particularly, but I know from working with it so much that the Ka for acetic acid is 1.8 times 10 to the negative fifth. So if I want to find the pH now, after the mixture of the base into the acid-base buffer, I simply use the pKa, which is the negative log of 1.8 times 10 to the negative fifth, and I add the log of the base, which is 0.318 molar, over the acid, which is 0.279 molar, and that should equal the pH. And the pH is equal to 4.80. Now if I go up to this picture, and there it is. As I calculated it, it said it was 4.80, but now I calculate it. The point being is buffers, what's the point of them? Well, by adding the same base to a buffered solution compared to water, I only see a change in pH of about 0.06 units, whereas if it was added just to pure water, the pH would change by a lot. So with that trusty little formula that I gave you on the last slide, you can calculate the pH of a buffer pretty quickly using the Henderson-Hasselbalch. It's always base over acid, and it's the concentration of base over concentration of acid. Now what's nice is, in a buffered situation, the two substances, base and acid, are usually going to be in the same liquid, so the same volume, and so the number of moles, the ratio of moles, is equal to the ratio of molarities. Something that might be able to speed up your process. Now, you've simply got a Ka value, so I can take the negative log of 1.4 times 10 to the negative fourth, and then add that to the log of the base over the acid. Well, I've got 0.12 molar acid, I've got 0.1 molar base, the base being the conjugate base of that acid, so 0.10 molar over 0.12 molar, and without you having to do any ice tables, simply calculate this. The pH is going to come out to be a nice easy number using the Henderson-Hasselbalch. The pH is 3.77. Make sure to keep track of your significant figures for pHs. Still only 2 past the decimal, since my concentrations were 12, and 0.10.
Moving forward with more problems, I'd like to talk a little bit about a couple of things you need to know that deal with buffers. One is called the buffer capacity. Buffer capacity is defined as how much acid or base a buffer can take before a drastic change in pH is observed. And so a buffer will be able to take acid and will continue to take acid until all of the conjugate base has been absorbed or used up. At that point, you'll see a spike, in this case, a drop in pH. We call that spike or drop a broken buffer. And so once the buffer capacity has been breached, you have broken your buffer. The only way to determine whether or not a buffer has been broken, outside of observation that is, if you're going to calculate it, you need to take and keep close track of the moles. So you need to know how many moles of the acid and how many moles of the conjugate base are in your buffer in order to determine at what point the buffer will be broken. So this is stoichiometry dependent. So what that means is that the more moles of the acid you have in your buffer, or the more moles of the conjugate base you have in your buffer, the larger the buffer capacity will be. Because as you drop in maybe some strong base that reacts with the acid aspect of the buffer, it will use up some of the acid. And you can start with 0.5 moles of acid and 0.45 moles of base, and you can essentially put in 0.5 moles of strong acid. But as soon as that acid is used up, then the buffer's broken. Excuse me, I meant to say base. So if you start with more moles, you will have a stronger buffer capacity. Now the other characteristic of a buffer that I want to talk about is called the pH range. And it is defined as the effective range of a pH that a buffer performs over. Now the pH range of a buffer depends on the acid and conjugate base, the common ion that you decide to use. Different buffers are effective over a different pH range. If you want a buffer that's effective over 10 pH, maybe for example, which is on the basic side of things, then you want to use an acid and conjugate base, and specifically the Ka and Kb are important for these to be effective over a particular pH range. And so you want to choose an acid based on its Ka or the Kb of the conjugate base to determine the effective pH range. And the final thing I want to talk about when it comes to buffers is something referred to as the best buffer. And the best buffer is, once again, subjective to the buffer that you create. But the best buffer is one that is equally effective on strong acids and strong bases. And what that means is that when you create it, you want to have equal moles of acid and conjugate base in your buffer. So in the lab, part of the pre-lab asks you, what would the best buffer be for the buffer that you're trying to create? And you need to calculate out the moles of each of the acid and conjugate base. Now typically the acid is going to have a molarity associated with it, whereas the conjugate base is a solid, so you'll have to calculate the number of moles. We'll assume that the volume of the conjugate base is negligible when you add it to the solid. Even though some of the solid adds volume, you just assume that there's small enough that it's negligible. So in order to determine that, you need to focus in on the moles of each the acid and the conjugate base. Quick moment, talk about buffer graphs. Basically what I want to show is the different kinds of graphs that you would possibly see when adding acid or base to a buffered system. And hopefully you'll be able to understand a little bit better what buffers are through graphical representations. Let's first talk about this graph. On the vertical axis I have the pH, and we're still going to measure the pH versus the amount of NaOH added in the form of milliliters. Now at first I'm going to start by adding NaOH to water. So this example over here is what the graph would look like if we began with water. Now the pH would begin at 7 because that is the water's pH. And the first data point would be at 7. And we would add a little bit of NaOH to water, and immediately you'd see the graph begin to increase. And the more you add, the more it would increase until eventually you reach a pH of 14. That's at which 1 molar NaOH is, that's the pH of 1 molar NaOH. So what I want to point out is that you begin immediately by climbing every milliliter or every couple of milliliters you add, but then levels off at 14, but never really exceeds 14. Now we're going to compare this to a situation where you add the same NaOH to a buffered situation. Now first of all, because we talked about on the last slide, we need to decide what the pH range of this buffer is going to be. And I'm just going to say we make a buffer that starts at about, or buffers at around, a pH of 3. And so our pH, our first data point, is going to be down here at 3 because that is the original pH of our buffer. That pH was determined using the Henderson-Hasselbalch equation. I mixed together an acid and its conjugate base. I knew the Ka of the acid. All of that information was determined to figure out that the initial concentration of H+, or the initial pH of the buffer, is at 3. Now as you begin to add NaOH, you're going to begin to increase, and this buffer will see a gentle or gradual slope. It won't be immediate like you saw with the water. And the reason is because this section of the graph, you're adding you're adding base to the buffer and it's reacting with the acid. So you're getting a little bit of an increase in pH, but not drastic like you saw on the other side. But eventually, you get to the point where your buffer breaks and you'll see a drastic increase right around here. Now the length of time that it takes depends on the buffer capacity, which we talked about also. The capacity is how much acid and how much of the conjugate base you really added to the buffer originally. So this amount of time changes depending on the capacity. But once it breaks, every drop of NaOH added will increase the pH pretty quickly. And again, it'll level off at about 14 because that's the maximum pH that a 1 molar NaOH solution would offer. And so compare these two graphs. This one starts out at neutral and blasts up to 14 immediately, where this one kind of hangs out, increases a little bit, and then eventually shoots up. And that's what a buffer will do. It resists the change of pH compared to just water. It will resist the change of pH until it's broken, until the capacity has been reached, and then it shoots up. Now let's take a look at what a graph would look like for the same buffer but with the addition of HCl. And first of all, you'll notice that it starts at the same pH as your blue graph, because your blue graph and your red graph should have the same buffer in it. But now we're taking that buffer and we're adding a strong acid. And you'll notice that as the acid gets added, it will gradually sink down, but eventually drop drastically once the buffer is broken. Now, like before, the buffer breaks once you've used up all the conjugate base in the buffer, where there's nothing there to soak up or react with the HCl. And at that point, you'll see a drastic drop. And eventually it'll level off down here near zero, because that is where 1 molar HCl, in this case, reaches its pH. The negative log of 1 is 0. The buffer capacity, again, depends on how much acid, or in this case how much base, was in the original buffer. So that's going to determine how long it took, or how many milliliters it took to see a drastic turn. But this is the graph of an acid with a buffer, whereas the blue graph you saw above is what it looked like with a base added to a buffer.
So this is a calculation type of problem that you'll get when you're trying to determine what the new pH is of after adding an acid or base, strong acid or strong base, to buffered solution. It's broken down into two parts: the stoic part first, and the second part, which is the equilibrium, or the Henderson-Hasselbalch part second. We need to use stoichiometry to figure out the new concentrations of the acid and conjugate base. And once we do that, we then can use those to figure out our Henderson-Hasselbalch numbers and thus calculate pH. Because ultimately, that's what we're trying to determine, is what's the pH. Calculate the pH of this solution after 10 milliliters of 0.3 molar acid is added. So let's start with the first step. Step 1, I'll put a line here. We've got to figure out how many moles of HCl are in this solution. So you take the volume of 0.010 liters over 1 times the molarity of 3.0 moles over 1 liter, and that'll give me the moles of acid. Now you don't need a calculator to calculate this. 3 times 0.01 is 0.030 moles
Of HCl.
Now what I like to do is set up the reaction that has the acid and conjugate base in it. First thing I'm going to do is check to see what my acid and conjugate base were, and it was acetic acid, and the conjugate base is the acetate ion. So we've got CH3COOH as my acid, and then the H plus, and then the CH3COO minus ion. I originally started with 0.300 molar, or moles, of each one of these. It was 0.300 moles per liter, or 0.300 moles. You want to get these into moles when you're doing the stoichiometry. You don't want to deal with molarity, you want to deal with moles. Because stoichiometrically speaking, this many moles of the HCl is going to react with the base, so it's going to take away or subtract 0.030 moles of your base. It's going to use up some of that. So my final moles of base are 0.270 moles, and every mole of base that gets used up creates that many moles of acid on the other side, and so 0.330 moles of the acid and 0.270 moles of the conjugate base. Now at this time, before I put these into Henderson-Hasselbalch, I need to calculate the concentrations. But as I said before, since they're going to be divided by the same volume, 1.010 liters, then the ratio in Henderson-Hasselbalch is the same. Remember, it's base over acid. It's concentration of base over concentration of acid. And since the denominators are the same in both the base and the acid, then it's the ratio of moles over moles as well. So if I take the log of base over acid, and I take the negative log of the Ka and add that to it, I will get the pH. So let's do this one step at a time. the negative log of the Ka, and I'll scroll up to get a closer look. Now I remember it, but just to give everybody a chance. It doesn't actually say it in this problem, but in the hint here, we talked about how when the moles of acid equal moles of conjugate base, the pH is the pKa. And if you notice, we got 0.3 moles of each. That means that the pH of the buffer originally is 4.74. So that's actually the pKa as well. And the pKa is 4.74. That was the pH originally. Well, I'm going to add the log of the base, which is 0.270 over the log of the, over the 0.330 moles of the acid, and that should give me the pH. And the pH is equal to 4.65. That's my new concentration after adding the acid. You would expect this to go down or more acidic because you're adding acid to the buffered situation. And it started at 4.74, went down slightly, but not too much. So the final concentration is lower than you started because you've converted some of the base to acid, so you have a higher concentration of acid than you do base, which is reflected right here in the Henderson-Hasselbalch ratio of base over acid. So in summary, you're going to have to do this a couple times maybe in your future. If you're going to calculate the pH after the addition of a strong acid or strong base, you got to take a closer look at the stoichiometry, how much of the conjugate acid and base are used up, and then use the resulting solutions concentrations to figure out the pH using Henderson-Hasselbalch. So make sure you follow these two steps. Do the stoic first and then the equilibrium second to get these. So thanks for listening.